because it's Vy, right?
Wait, let me construct what we're looking at. So we are looking at I should not construct this way. So this is part of the main structure. Okay. So the element we are going to look at this is element A, right? So element A, so what we have on element A is bleh. So we have, I need to find our transformation. So this is our Y, this is our X, and based on right hand rule, this is our Z, right? Right. So this direction is our Y direction. Okay. So so we realize that the shear flow is going this direction. This is with depth. Okay, so this is our thickness. Okay, so when we draw the element out, so this is our element A. Okay, this is our element A. So based on the transformation, so the shear stress is doing this, right? So by looking at that, so this is the shear, the plane intersecting. Okay, so this plane is intersecting the x-axis, right? Because if I draw the axis over here, x, z, and y, or y go to the side, right? The intersecting axis to the plane is x, and the shear and the shear force over here, which is going upwards, is equal to the z. And for this one, the shear intersecting the plane intersecting the axis is the z-axis, and this is going to be in the x direction. Is that okay?
Where I'm confused is, like, isn't the shear force in the y-axis?
No, the shear force is in the x-axis. I'll tell you why. So the shear force, right? So I draw complete 3D again.
Oh, is it because of the shear flow?
Ah!
Okay. Okay, sorry. Yeah, okay, now I get it.
I
Sorry.
like that. No, don't sorry. I make the same mistake because once it's shear flow, you have to be really, really what? Careful, right? No, you don't be sorry. Listen, I make the same mistake. Okay, so that's why we cannot, by looking at the force, we cannot look at this force. Okay, we cannot look at this force. All right, we cannot look at this force and say, okay, this will be zero, that will be zero. No, you can't say that. You have to construct your what? Your shear flow. Okay, that's a good one. Okay, that was a really, really good question. Okay, I should have thought about that while teaching you guys also. But you asked a great question. I like that. Okay. Hey, any question asked? Okay, always the few people ask, the rest are quiet. Come on. But don't ask so much that I have no time to teach. Yes. Okay. So from here, right? So let's see what we have. Okay, let's see what we have. So last week we had, okay, so last week, right, I'll take this, I'll copy this. Right. Okay, last week we had this, right? So we also found, I also would like to paste this, right? I'll take this diagram. I want you to see something. Okay. And then, sorry, today is a bit messy on me. Right. So this one we are looking due to Vx. Right. Then we construct another diagram today. Right. So this is today. Okay. This is our Vy. So our shear xz is equal to shear zx, and we had a value of, I do apologize for flipping here and there, okay. 6.047, and I do apologize, it's best to put your direction. Okay, going this way. So 6.047, right? 6.047 times 10 to the power 6 Pascal, and it's going this way, right? The other one is equal, the one we just calculated is equal to 4.439. Okay. So we have two of them acting in opposite direction, right? So I did not know which direction this is going initially. I have not a clue. Okay, I'm telling you this now. I have not a clue. That is an assumption that I made, okay, that is going to flow in that direction. I just make that assumption, okay? So now to superimpose what is going on, right? So if you look at the direction over here, right? The direction for due to Vx, okay, due to Vx, this direction, the shear is going in this direction, right? Is going in this direction. And this direction is 6.047 megapascal. Okay. And then the other one, it got opposite, right? The other one that we did, okay, the shear, right, is what? The shear is 4.439. Okay. So I write down this is due to Vx. This is go to Vy. So if you put both, if you add up both of them together, right? So the direction now goes opposite, right? Because the Vx value is 6.047 and the Vy is only what? 4.439. So what I'm trying to say down here, we got it wrong. I repeat again, we got it wrong. Okay, the direction is wrong. Okay, direction of the shear is wrong. So the right value or the right direction goes like this. Okay, so it's just simple addition. Okay, so now we are just doing simple addition. So we know that we have a force going that way. So this is 29.852 times 10 to the power 6. Okay, and then this is the correct shear direction, right? So this is equal to so the shear xz is equal to shear zx. This will be equal to 6.047 minus by 4.439. So this will be equal to 6.047 minus 4.439. This is equal to 1.608 times 10 to the power 6 Pascal. Okay, you understand, right? Makes sense, yes or no? Right? Okay. So this is what I mean.
I have a question.
Yes.
So for the how did you know they were either going right or left, like based on Vx or Vy?
Say it again.
Like, you know how you got 6 megapascals and like
Yep.
4 megapascals? How did you know which one was going right and which one was going left?
So this force Vx is going this way, right? So the shear flow will go from what? Will go this way, yes or no?
Yeah.
Yeah, so that's one direction. And the other one, the Vy, the shear flow is from the bottom, and then you start, oh, sorry, the shear force is from bottom, and this is how you construct your shear flow, yes?
Oh, okay, okay.
Right?
Yeah.
Hey, Miriam, I know you're really good in shear flow. What happened?
I drew the arrows wrong.
Oh, okay, okay. I thought it was due to Dr. Cotton. He confused you guys already because he did not do the second law of thermodynamics, right? I'm just kidding. Oh, no. Thermodynamics don't have fluid flow yet. It's fluid dynamics, right? When are you guys going to do fluid dynamics?
Next year.
Yeah, you'll be fine after you learn from this, okay? Okay, so that's how we get the direction. So from here, we know that the correct direction is this way now. Yes?
Can I clarify something quickly?
Yes.
So for the tau xz and tau zx, you define the x and the z based on purely the shear flow, correct?
No, the shear, yes, is sorry, you're right.
Yeah, so you get the x and the z from the direction and the intersecting plane of Q.
Wait, there's a lot of words in there.
So like if you have tau xz, you get the x and the z based on Q in which direction it's going and which plane it's intersecting, correct?
Yes, yes.
Okay, thank you.
Like what I mentioned before when Mira was asking, right? I used this rule, okay?
Yeah.
And I think I explained this last week, and those of you that have taken 3CO3 with me last term, I also been through this, right? Okay. So if you're not clear, I think last week we talked about this also, okay? But I clarify again, okay? Right.
Thank you.
Most welcome. Okay. So in your term test, okay, I just want you all to do up to this, okay? I don't want you all to solve it yet, okay? Because for you guys to be able to solve it, I need another like 3 hours of lecture. And I understand that tomorrow I have 2 hours, but I feel that it's not fair that all of a sudden I throw another monkey wrench into your problem, and I don't do that to you. Okay, so the next thing we're going to do, we are going to look into element B. Okay, we're going to find element B. Okay, so we're going to construct element B. Okay, stresses. Okay, so where element B is, if you refer to your lecture last week, so I'm going to cut and paste again, copy. Okay, so now we are going to see what is going on our element B. Okay, so the stresses that we have analyzed from here, right, from here is still valid. Okay, the stresses will be the same. Okay, so I'll try to copy this whole thing because I don't go back and forth, because I'll go bananas. Some of you are there already. Okay, so I'm going to hope this works. Oh shit. Sorry, it's not you. It's not you. Okay, it's the user. It's me. Software is fantastic, but it also have a lot of like bad points. Okay. So okay, I'm going to I've done this before, but it crashed so often. Okay, so element B is over there. So element B. So if we look at what we had last week, okay, what we have last week. So element B. So let's look at the normal stresses first. Okay, let's look at the normal stresses. So we know at element B, you're going to have a PZ. Okay, so the axial load of minus 100. Okay, so I'm going to write down, we have a minus px of minus 100 times 10 to the power 3 Newton. Okay, then we are going to look at our stress in our my. Okay, so there's a moment in y that element B is in tensile. Okay, so moment in y, you have 9600. So you have moment in y is equal to 9600 Newton, right? And this will be in tensile. Okay, so we got that last week. Okay, then we are going to look at Vx. Okay, Vx at element B. Okay, we don't know yet. Okay, so because we have to construct the shear flow. Okay, and Vx is equal to 16 times 10 to the power 3. And then what else we have? We have, so Vx we don't know yet. And then we have our mx. Okay, and stress B for mx is equal to 0. Okay, so we know that mx Okay, so mx for this case will be 0. Okay, not 0. Sorry, it will induce is at the neutral axis. So it'll be 0, but there's a value. Okay, there's a minus 22750. Okay, so minus 22750 Newton meter. And what else? Do we have a Vy? Okay, so we have a Vy of 25,000 Newton. Okay, so we have a Vy. Now, this is where you see that I did not look at this problem like you guys until today. Okay, but I know I don't need to analyze because we have all the information down here. If it is done properly, okay, if it's done properly, you have all the information down here already. Okay, so that's why I want you all to have the habit of writing what element is under what sort of stress, tensile or compression. If you're not sure, say you're not sure. It's fine because there are some things that you have to look at thick wall, or you cannot assume that it's thick wall. When you go thin wall analysis, you have to think.